next speaker. Ilja, are you online?
Yes, I'm here.
Okay. Okay, so our last speaker of today, Ilja Kuzborskij. So Ilja is a research scientist at Google DeepMind, and he's working at the foundation team. So the foundation team working problems for RL and try to understand foundational theory for RL. And in Ilja particularly focus on problem-dependent analysis and how to design learning algorithms in the setting of batch RL, in the setting of with partial feedback, and also in with non-parametric models. So Ilja will talk about batch policy evaluation with confidence intervals.
Thank you, Mandy. It's a pleasure to be here. This talk is not going to be about the full-blown MDPs. I will step down a little bit. This is going to be about contextual bandits, and what we care about here is confidence intervals for contextual bandits in the batch setting, and non-asymptotic high probability. And this is joint work with Claire Vernada, Andras, and Csaba. Okay, let's start from the contextual bandit model where we're looking at here. We will have a context space and the probability measure over context space, which is potentially continuous. It's a measurable continuous space. We will have a probability kernel, which will give us reward function, given the context over some finite action space. And in this particular model, we will also assume that the behavior policy is known. And the protocol is the following. An agent observes a tuple of triples, which are context action rewards. All of them are independently sampled. And the agent follows some randomized target policy. So the fact that all the elements in the sample are independent suggests that behavior policy is going to be stationary. So we will not assume that it's produced by some bandit algorithm, but rather that it is produced by the batch algorithm trained on the large amount of data. And this setting is relevant, for example, in industrial applications where you have huge data sets. And now, what do we care about? If we come up with a new policy, we want to give some estimate, uncertainty estimate for the value, which is defined as in this sense. And there are many ways to do that, and one of the standard way that you have heard about before is the importance weighting. Importance weighted estimator which is a weighted average of the importance weights and rewards. Rewards are, by the way, assumed here to be bounded. This estimator is unbiased, but unfortunately, very often in practice, it suffers high variance, and it's not hard to see why, because if we imagine some disagreeing policies with a little overlap, this will likely result in distribution of importance weight, which is heavy tail. There are many ways to deal with variance of estimators. One popular way to patch this up from the point of view of reducing variance, but in terms of rewards is doubly robust estimation, where we try to correct for the variance in the rewards through reward modeling. Typically, it's fitting this function eta hat on the held out data sets, regression of rewards. And the focus of this talk is going to be the self-normalized importance weighting estimator, where this aforementioned weighted average is normalized by the sum of the weights, and practically this often results in reduction of the variance. This is known to be biased, however, under some appropriate assumptions, asymptotically unbiased. And the intuition, why do we care about this? Why the variance might be small here is by looking at this the small neat inequality, which comes from the Efron-Stein's inequality. Essentially it can be represented and it tells us that the variance is controlled by the sum of the squared weight, the reciprocal of the sum of the squared weights and the square of the sum. What does it actually mean? It means that in some cases, depending on the distribution of the weight, we might capture different regimes of the behavior of the estimator. For example, if two policies are perfectly aligned, are identical, this will be of order 1 over n. If they're completely non-overlapping, we will approach 1. And all the intermediate behavior is captured by this quantity, which in Monte Carlo theory is called effective sample size. Now, in a sense, this is a nice instance-dependent quantity, which we would like to depend on in our analysis, and which has to be and which ideally has to be evaluated from data. Now, little idea on how the estimation of the value might look like here, and to recap what we're after the high probability lower bounds on the value, where we assume epsilon to be small and data dependent. Our confidence interval small and data dependent, and the usual analysis undergoes three. And the usual analysis undergoes decomposition into the 3 parts. Here, we will get rid of the randomness in the context by separating the concentration of the context. We will look at the bias of the estimator and the concentration of the estimator. And for now, I will focus only at the concentration of the estimator, because this seems to be the most challenging part for this type of confidence estimation, and the dependence on the variance or on this kind of quantity that we would like our confidence bound to depends on will come precisely from the analysis of the concentration of the estimator. And to be more precise on what do I mean here I'll make a brief recap of what is concentration and why the standard tools with dealing with the concentration are not enough. So whenever we have a sample of independent random variables sampled from the same probability measure, in the concentration, we care about how a fixed measurable function of this sample deviates from its mean, and understanding how it happens comes from the analysis of the tail probability. It's a pretty standard thing. One of the classic concentration inequalities, as an example, is a Markov, and the workhorse of the computer science and statistics are Hövding and Bernstein's inequality, which essentially work for sums of independent random variables where random variables have a sub-Gaussian behavior. Or in practice, typically assuming that random variables are bounded. However, if we will go back quickly and look at what are the requirements in stating our confidence interval, we quickly observe that things depend on unbounded random variables such as the importance weights. Note that the behavior policy might be arbitrarily close to 0. And this effectively excludes things. It excludes the use of standard tools. If we want to do things really cleanly. Of course, we can introduce all kind of tricks and hacks. For example, truncation of the importance weights is a pretty popular tool in the literature, but it has its own limitations. We introduce truncation, we introduce an additional bias in the estimator, which we have to control for, and this results in some hyperparameter tuning. And we would like to avoid that. Variance is important. Our bounds should depend on the variance, as we saw before. In case of importance, self-normalized importance weighting, it's essential because we hope to capture this small variance, which appears often in practice. Sometimes estimator is simply not a sum. Like in the case of self-normalized importance sampling, we have a self-normalization, which introduces dependencies. Right, so this is briefly to have a picture of the same challenges, but in the context of the self-normalized estimator. And if I would revisit the concentration, the toolbox of concentration inequalities that are available to us, the first thing which would be possibly an answer to that are the bounded difference methods, which try to look at the concentration of arbitrary functions, of arbitrary measurable functions in terms of their sensitivity to small perturbations. What do I mean by this? Imagine that we have the original sample, and I resample one of the elements freshly from the same distribution. And what I want to say at the end that at the end this function is not sensitive to this kind of resamplings. And this is at heart of the classic, again, at the classic Efronstein's inequality, where the variance intuitively, it's also pretty clear intuitively that the variance is controlled by sum, or in this case, expected sum of the squared perturbations of that function. So ideally, we would like to get confidence interval, which depends on something like this without introducing much more of additional assumptions. Again, a standard tool is a bounded difference inequality here, or McDiarmid's inequality, where we again look at the Efronstein's variance proxy. We capture some perturbations of the functions of the function at hand, and we quickly observe that the inequality is quite pessimistic because we do that in terms of the supremum over all the samples, and that supremum over supremum of the variance proxy gives us the rate. Clearly, this is not always enough because recall that essentially our importance weights are unbounded, and maybe we also want to capture variance. So it doesn't seem to be the tool that we would like to use at the end of the day. Now, that's right. Neglects information about higher order moments, and the answer to that could be a more powerful tool, like recent developments in concentration inequality, which gives us this beautiful exponential version of Efronstein's inequality, which basically tells us that to control deviation of the function from its mean, or the moment generating function, we can control it in terms of the moment generating function of the Efronstein variance proxy. So, and that seems to be sufficient. Recall that Chernoff bound would immediately give us concentration inequality if we're able to control the tails of the Efronstein variance proxy. Now, this is a bit challenging to use at times. Can we get something more user-friendly where we can plug in our estimator and get concentration bound that we want? Indeed, by going through standard control of the moment generating function of this this thing, which is a Efronstein variance proxy, we can get something like that, which indeed will depend on the Efronstein proxy, plus some terms which come from the control I just mentioned, and this is upgraded. It's more sophisticated version of the Magdaram's inequality, because now instead of controlling first order bounded difference, we need to control in some way second order bounded differences through this scary looking inequality. And again, we encounter supremum over samples. So it suggests that this might be a bit challenging if we want to get something instance dependent that depends on the distribution of the importance weights. So these constants in practice would have to be data dependent, and typically we would need in one or another way boundedness of the random variables to achieve that. Can we do something even more user friendly? Well, it turns out that we can, if we consider slightly different version of the Efronstein variance proxy in the following form. It's semi-empirical proxy, which is semi-empirical because we have this conditional expectations in the summation. So it partly depends on the distribution and partly on the data. But the trick of the eventual use of this would be to get away from the parts of the distribution that we don't have control over, and live with something that we can with the expectations that we can actually compute. And this allows us to prove this concentration inequality, which is surprisingly light on assumptions. So the function here needs to be measurable. We do not explicitly control the tail of the function of the sample, but the control is implicit in this variance proxy. So whenever we want to control particular function at hand, we need to control this semi-empirical quantity, right? And indeed, using under making more assumptions, we can recover the standard forms of Bernstein's inequality and whatnot. Now, how does it? What can we do in terms of the value of the uncertainty estimation here? Value bounds for our weighted for our self-normalized importance weighting. And it turns out that we can prove the following. It looks a bit scary at the first sight, but I will go through all the terms. And the first thing to note here is that this depends on this Efronstein variance proxy of the self-normalized estimator and the bias, and both are data dependent and both are computable, even though they involve expectations. Note that we have conditioning on the context, so we don't need to know distribution of context. We don't need to know distribution of rewards. The only thing we need to know is the distribution of the weights, but it is known to us because we have assumed that the behavior policy is known. Now, computationally, this might be a bit challenging, even for finite action spaces. But at the end of the day, we can approximate this using Monte Carlo simulation, and as we will see in the numerical experiments, this works pretty well. Now, if we look closer at the variance proxy, it is indeed very similar to what I was talking about at the beginning of the talk. Indeed, it captures the effective sample size of the self-normalized estimator, and through this bound, we can have all kind of different regimes depending on the overlap between target and behavior policy without making any explicit assumption about overlap. And no truncation is necessary. The bias term is a bit trickier to come by, but the main message behind it is that it's a multiplicative bias, and it approaches one for easy distributions, for distributions which are not skewed, and therefore this bound becomes tighter and tighter. Now finally, there is a term which comes from the control of the context, but it's just a Hoeffding's inequality, because value in our case is bounded, because rewards are bounded. This is pretty easy to see from the analysis. Right, and so yes, this I already mentioned. So how does it work in practice? Even though it looks a bit hard and not interpretable, everything is slightly harder to interpret compared to more pessimistic bounds. But how does it work numerically? Well, imagine this first synthetic simulation where we're given two policies and the means to control of their misalignment. These are effectively Gibbs policies, which are focused on two different actions, and tau temperature will control the degree of the misalignment. And comparing to bounds, to confidence intervals, which use truncation of the weights, we can see that even for relatively large sample size, we can always come up with higher degree of misalignment where truncation will fail. But the data-dependent nature of this Efronstein bound allows us to still to still estimate value reasonably well. So the value is a dashed line. We have a sample size and the convergence to the value, where the Efronstein bound is the one on the top. Now, what about the more realistic cases? Well, yes. So it's another view on the coverage of the bound. We can do the same. But instead of varying the sample size, we can vary error probability and look at the different standard tools with the truncation, standard bounds with truncation, and we see that Efronstein bound becomes somehow numerically closer to the actual value sooner for this smaller error probability. Now, what we largely care about in practice, and which of policy evaluation can be very good tool for, is of policy selection. So I'm given data set and a finite set of candidate policies. How do I select the best action based on some estimator? And the estimator here is in the colloquial sense. So estimator can be confidence bound. I pick is a rule for selecting my target policy. So it can be also thought of as a lightweight version of policy optimization, where the class of policies is finite. Again, let's look at some non-synthetic experiments in this case, where the setup is very simple. We have ideal policies and two policies which are fitted on the data using gradient descent with respect, in the first case, with respect to by maximizing the value with respect to importance weighted estimator, And the second one is with respect to self-normalized estimator, just like shown here. And the goal is to see whether a confidence interval will allow us to deal with overfitting, which is induced, well, perfect fitting, which is induced by these estimators, and whether other estimators such as the ones, rules such as the ones which do not use confidence intervals, which will actually fail. Even though our target policy is stochastic, we pick rather small temperatures, so that it becomes almost deterministic to have some idea on more realistic setting, because in practice policies, bandit policies in recommender systems, for example, are often deterministic. And indeed, for the small sample size, we quite often see that many bounds which rely on truncation or non-hyperability bounds are vacuous and decision cannot be made reliably, or they go for suboptimal policy, whereas more data-driven Efronstein type bound with respect to self-normalized estimator performs really well. And as expected, as sample size increases, they all catch up, and we are able to really to select ideal policy in all cases. But again, as we saw from the synthetic experiment, even for a very large sample size, you can come up with a problem where the overlap is really low, and then many of this can fail even for large sample size. Now, I have a couple of minutes. I guess I could briefly revisit the proof, go for the proof of the inequality, and just briefly mention some techniques which are used here. As I mentioned before, concentration of context is just Höbding's inequality by observing that the value is bounded, and we have to deal with sum of independent random variables. The bias, the control of the bias is rather interesting here, because rather than saying something asymptotic, we go for a non-asymptotic version of it. We use this association inequality, which is known as Harris inequality, which simply says that we can control the expectation of product of some sums of random variables if there is a non-increasing and non-decreasing coordinate-wise behavior in each function. We can split that, and indeed self-normalized estimator is one of those cases where you can actually do that, and then we effectively split it into importance weighted estimator, which we know is unbiased, and the multiplicative bias, which will be governed by by how skewed the distribution of the weights will be. Again, this can be computed from data, because distributions of the weights, the distribution of the weights is known. Now, as the proof for the main concentration inequality, this draws heavily on the standard analysis of the Mark-Darabin's inequality and the analysis and the proof of the Efronstein's inequality with a bit of self-normalization. So unlike the case, so essentially to prove everything here, we need to prove that the function and its that the function of interest and its Efronstein's variance proxy form a canonical pair, as it is known in the self-normalization theory, and then we pretty much can use the standard results of the Lapény and others to arrive at the concentration inequality that we use here. And the interesting bit is, how do you do that? Well, it turns out that a standard dupe-martingale does the trick. And this is really similar argument of how Efronstein's inequality, the proof of the Efronstein's inequality goes through. Yeah, I would like to conclude with some take-home message. So this seems to be numerically non-vacuous for the value estimation in contextual bandits. This is for the self-normalized estimator, which is known to have a low variance in practice. And it seems that these bounds really are able to capture this fact and might be useful for a practical confidence bounds, non-asymptotic, high probability ones, and some challenges. This, of course, limitation is that we need to know behavior policy. It has to be static. So, for example, behavior policy cannot be generated by the bandit algorithm that we ran in the past. And an obvious interesting extension of this is of policy optimization. And there is some work that we were trying to explore in the pack-based setting by having some uniformity over policy class. Well, in this case, in the pack-based case, over the probability measures over the classes, over the policy classes. And yeah, I believe that's it. And thanks.
Thank you, Ilja, for the beautiful analysis. So I have one question for clarification. So it seems that analysis is really for the tabular action case. Is my understanding correct?
It's a finite action case, but the context space doesn't have to be finite.
Of course. And is there any notion of optimality for the confidence intervals?
No, it's we don't have bounds which would show that this is optimal, but we just rely on some numerical evaluation for that. Yeah.
But numerically, does the confidence bounds give you something like some asymptotic convergence in probability to the right interval? Is there something like that can potentially be proved?
I think this can be explored, but I cannot say on the spot if this has this optimality.
And also, if the policy is not known, and then the weights are not known, right? So in that case, if we want to get similarly tight error bounds, does it mean that we need to estimate the policy to the extent that all the numerical values have to concentrate very nicely? So
right.
I mean, a lot.
Yeah, we would need to have something tight. We would need to have control of the approximation of the behavior policy reasonably well. Yeah, and it feels to me that it will defeat the purpose of the entire bound if you would do really pessimistic analysis of that. So I guess one of the challenges would be to control this approximation error by with the similar data dependent attitude, right?
Right, and also, so I think also I got lost. So what was the final assumption that were needed?
The final assumption on the concentration, concentration bound. So the let me go back to it. Right, this one. Right. So the function f has to be measurable, and that's pretty much it. Right. And this is the bound which holds with respect to free parameter. Right. So ideally, you would like to tune it in some way, but apart from independence is crucial here. But apart from that, there are no assumptions.
Okay, so we really just need V to be well defined.
Right, right. So in the standard concentration, you typically make assumptions during the analysis of the moment generating function, right? And here this is deferred to the analysis of this V. Right? So it's up to user of the concentration bound how to bound this V. So and we don't make this decision during the analysis of the moment generating function.
Yeah, very nice. I think Gurgley has a question in the chat.
Yeah.
Can you see it in the Q&A button?
Just a second. Yeah, could you? So about the term, okay, let me. Yes, I see. Let me share my screen again and go back to the point. Right. So the question was about this term, right? And this is so we can see that this term is it's known to us. It's a part of the data set. We condition on it, and this term is not known, but it's distributed according to the same distribution as WK, right? And this is not known, and we need to compute expectation, and we effectively compute expectation with respect to this, and this is yeah, I believe that a similar version of this kind of inequality can be shown, where instead of the replacement, because here we have a replacement, right? So if you think about the invariance proxy, here we have a replacement of the element in the sample. A similar version, I think, can be shown for deletion. But then again, this will not make concentration inequality completely empirical, because we will depend. We will have conditional expectation only with respect to W's from 1 to K, and all the remaining ones, and we would compute expectations with respect to all the remaining ones, right? And I think, yeah, the second part of the question was, could there be a fully empirical version? A fully empirical version would be the one without this expectation here. And I tried to look really hard into it, and my understanding was that this is, I don't know how to do it, but clearly something like that is possible if we make further assumptions on the boundedness. Like we can get empirical Bernstein's inequality, and similar bounded differences inequalities with some proxy, with some variance proxies are also known. I think, works of Andreas Maurer, but yeah, I think we would need to give up something and assume more to get fully empirical version. And did you test? Yeah, I mean, variation. Yeah, I'm not aware of any. I don't know of any ways how to do this fully empirically. So, yeah, no experiments on that part.
Okay.
Mhm.
Thank you. Do we have any more questions for Ilya or for Diana? Emma, Sean, is there anything you want to add? Okay, Sean is walking to us.
I have to turn off my mute button. No, I mean, only that I'm looking forward to studying this. I mean, there's a lot of beautiful techniques here. That's all I don't have any questions right now.
Great. Okay, so we are going to conclude here, and we're going to see you again tomorrow. So the gather time will start at 8:30, and talks will start at 9 a.m. Pacific time. And thank you to all the speakers. Thank you. All right, see you tomorrow.
So,
Bye bye.